Hello, happy Tuesday. All right, so we're going to continue on with Unit 5, where we're analyzing linear, quadratic, and exponential functions all together, one big happy family. Today's goal is pretty laid back. We're going to do a little graphic organizer so that you have everything in one spot. If you don't have a printer, no problem. Just grab a clean piece of paper, boom, and label it up linear, quadratic, exponential so that you've got them going side by side. Okay, so getting started, let's talk about what that equation is. All right, so for linear, you're going to have y equals mx plus b. All right, so some friendly reminders on the parts here. M is slope, so that is your rate of change. Notice it's attached to a variable because it changes, right? It's rate of change. The b is the y-intercept, right? That's where it crosses on the y-axis. All right, so then the next equation that we got into in February, March, was quadratic. So the quadratic equation looks like this. Y equals ax squared plus bx plus c. But there was also another way to write it. Do you remember when we would complete the square? We created a monster so that we could see what the vertex was real quick. So anywho, quadratic could also be written like this. Y equals ax minus h squared plus k. Right? Remember, that allowed us to see the vertex real clear. So this first one is called standard form. The second one is vertex form. All right, and then the last few weeks we were looking at exponential functions. Those equations look like this. Y equals a b to the x. And sometimes there was this additional plus c over here. All right, so let's get some labels. The a here is your y-intercept, right? It's called the initial value. So it's where it crosses on the y-axis. Then you've got the base, and that's your growth factor or your decay factor. So if it was a base of 2, that means it would be doubling every x value. Then the c, whatever was added here at the end, was the invisible line. We call that the asymptote. It's a weird word to spell. Asymptote. It's a weird word to say too. I feel like I'm cussing. Anywho, that's the invisible dotted line, right? The electric fence that your graph gets closer and closer to, but it's not allowed to cross it, right? If it crosses it, then it gets shocked. All right, so the graphs. Linear equations, we know what those look like. All right, those are just those straight lines. I mean, maybe they're flat, maybe they're vertical, maybe they're negative. So there's a lot of different ways these lines could go. Quadratics, those are the parabolas. I'm going to put that right here. Parabola. Parabolas, they're either going up or they're going down. All right. And then exponential functions, they either grow or they decay. All right, so there's growth and then there's also decay. Okay, so when we have to identify these different graphs from a table, which is what we're really going to get into tomorrow, this is just an overview. When you're identifying from a table, these linear functions have a pattern. It's either addition or subtraction going down the y list. All right, so you'll look at that output side, the y's, and you'll see, is it adding by the same number or is it subtracting by the same number over and over and over? If so, that's how we know it's linear. I want to skip all the way over here to exponential because that one's pretty fresh. When we were looking at the tables for exponential, it was multiplying, multiplying, multiplying in those tables. So for tables, you multiply to get next term. So you'll look at that y list, and if it's multiplying, that's exponential. Again, if it's adding, it's linear. If you're multiplying, then it's exponential. Okay, so quadratic, that one's a little bit more tricky. All right, this one you have to look at a second difference, and we've never done that before. It's the same second difference. So we're just going to write it down for now, and then tomorrow when we start looking at these tables, you'll see what I mean by this. All right, so same second difference. But a good rule of thumb is if it's not adding and subtracting, if it's not multiplying, then it's most likely going to be this little guy. Okay, then we've got the average rate of change. That's a fancy way of saying slope. The formula for slope is y to the sky. And then x's are on the bottom. So you're finding the difference on the y-axis, and then you're finding the difference on the x-axis, and that lets us know what that rate of change is as you're going along the graph. For linear, you're going to have a constant rate of change. Constant rate of change. All right, we did a lot of those graphs before we went on quarantine, right? We would do our rise over run, rise over run, rise over run. It was constant all the way through. However, when we get into quadratics, it's not constant. This side, for example, is negative because we're going down, and then this side is positive, it's going up. All right, so we have these different rates of change going on. So instead of saying it's a constant rate of change, we say it's an average rate of change. No worries, the formula is still the same. We use this guy, and it's just averaging that rate. Same over here. For exponential, it's an average rate of change. Meaning, depends where you are on the graph as to what your answer will be. But for a linear function, you could be anywhere, and the answer is the same. All right. Domain and range. Domain is going to be easy for this. The domain is all real numbers all the way through. So I'm going to put D for domain. It's all real numbers. Domain, all real numbers. Domain, all real numbers. So we could put anything in for x into these equations that we want. We could put -2. We could put 1 million. We could put 1/2. We could put 2.2229. See there? So we could put anything in for x that we want. So I'm going to add right here, domain, that's your x value, right? That's the input for your equation. The range is your y values. That's your output. All right, so your range, let me put an R for range. When we're talking about linear functions, the y's could be anything, all right? It is, again, all real numbers. But the range for quadratics gets a little bit more picky because your parabola is either going up or it's going down, right? It's not doing both. So we can't just be anywhere that we want to be on the y-axis. So your range is going to depend on what that vertex is, right? How far up did you shift it for that k value? So down here, let's see, we would put... Gosh, there's a couple of things I need to squeeze in here. If it's a positive A, right, so meaning in the beginning, positive A, that means it's opening up. So I'm going to put positive A. Then your range would be anything greater than the K. So you would say y is greater than or equal to K. On the flippity flop, if your leading A was negative, right, if this A in front was negative, that means your parabola is going down. So your y would be less than, right, because we're going down. So if we have a negative a, then your y is less than that k. All right, and we technically learned it. I know it was a long time ago, and we'll be reviewing that over the next few days. Okay, and now the most recent is exponential functions. So for your range, it's kind of the same idea. If this a in front is positive, then it is going to be on the positive side of the y-axis, but you have to watch out for the asymptote. So again, if we have a positive a, we're going to say y is greater than that c, right? That c in our equation is the asymptote. Notice I didn't say it could equal it. Over here, it could equal the k in this equation right here. But over here, it can't, right? It's that invisible dotted line that these graphs get close to, but they don't touch it, right? They don't touch it. Okay, so then if a is negative, that means it's flipped upside down, had a reflection. So we would say y is less than that asymptote. All right. end behavior. So what's going on the ends of your graphs? So let's see. The notation for end behavior can be a little bit overwhelming. It's very, very fancy. Take a look at this. We would say as x approaches infinity. So imagine an x and a y-axis. So if x is going to positive infinity, what's happening on the ends of your graph? Well, if your graph is positive, then it's heading up to positive infinity. It just keeps growing and growing and going and going. So we would say as x approaches infinity, y also approaches infinity. And if we go to the negative side of our number line, right, if we go to negative infinity, right, if we're going this way, which way does it point? It points down forever. So we would say x approaches negative infinity, then y approaches negative infinity. All right, so the end behavior for linear functions go the same direction. If x is positive, y is positive. If x is negative, y is negative. All right, parabolas are going to be a little bit different. The ends are both going up or they're both going down. All right, so if we have that positive a, we would say as x approaches infinity and as x approaches negative infinity, then the y is going up on both sides. All right, so that's up, up. All right, we're going to positive infinity, positive infinity. If your a is negative, all right, so as we look at both sides of our x-axis, your y's are pointing down. So we would say negative infinity, negative infinity. Let me draw a little picture. All right, so we're going down, 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 baby, right there. Okay, so again, it's all about that leading coefficient in these equations. If a is positive, it's up, up. So we would say positive infinity, positive infinity. If a is negative, then it's going down, down. So that's going to negative infinity, negative infinity. All right, and then last but not least, we've got the end behavior for exponential. Okay, so as we go to the right-hand side of our graph, we would say y also goes up. All right, so as we're going to the right, the y is, boom, going up. If we went to the left-hand side, whoops, y approaches, let's see, we would say the asymptote. Now I could have put the letter C like I did up here. Okay, so let me come up here. So as we go to the right, it approaches infinity. And then as we go to the left, it's going to get closer and closer to this dotted red line, to your asymptote. That's if it's growth, right? This is for growth. But if our equation does this, right, if it's decaying, as we go to the right-hand side, the graph approaches that red dotted asymptote. So y approaches asymptote. And if you look at the left-hand side of your graph, negative infinity, all right, so on the left-hand side, it's shooting up. It's going, woo, up to infinity. So our y goes up. All right, so that would be for decay. All right, a lot of thoughts thrown at you for today. That's enough for now. Tomorrow we'll start practicing all these little details. See you later.